Lesson 1.5b, even and odd polynomial functions. So it starts out by telling us if a linear factor x minus a is repeated n times, the corresponding zero of the polynomial function has a multiplicity of n. So what that's saying is, like, if I have this factor, and let's say it's x minus 2, and it's here twice. Remember, to find it 0, we set it equal to 0, and we set each factor equal to 0. And then we solve them. Well, we would add 2 on both of these, and so both of these we would get x equals 2. So we could say that the 0 is x equals 2, and that it's got a multiplicity of, it's there twice, so 2. All right, now also though, notice we could have written that as x minus 2 squared. So that little exponent up there will also help us know the multiplicity of the factor, and that gives us a multiplicity of the corresponding 0. All right, so if that real 0 of a has an odd multiplicity, so if it has a multiplicity of 1, 3, 5, 7, 9, the graph of f will cross the x-axis at x equals a. So it's going to cross at that 0 if it's odd multiplicity. If f has a real 0c of even multiplicity, then the graph will bounce, be tangent to the x-axis at x equals a. So I call it touch and turn. So that's where we get that quadratic lick. So if it has an even multiplicity, we're going to come up, we're going to touch that x-axis, and then we're going to turn and go back the other way if it has even multiplicity. Real zeros with odd multiplicity, but where it's greater than or equal to 3, will have a point of inflection on the x-axis. So they're going to have that little S-looking curve that a cubic has. So what's saying there is, if I got my x-axis here, and let's say this right here is my 0, if it has odd multiplicity, we know it's going to cross, and if it's 3 or greater, then it's going to cross a little curve there, and that point is going to be your point of inflection, because notice down here it's concave down, but up here it's concave up, or it could have been upside down, so it would be opposite. All right, something else about even and odd functions. Even functions are symmetric to the y-axis. So if you look at this first example here they give us, notice both of those, the y-axis cuts our graph in half. It's symmetric to the y-axis. Odd functions are symmetric to the origin, and this one's a little bit harder to tell, but when it's symmetric to the origin, that means if you take one point on your graph and you reflect it across the x and the y-axis, it's still going to lie on itself. So like this point that I just marked here, if I go across the x-axis, I'm over here, and then if I go across the y-axis, I'm on that same graph. Same thing here. If I cross the x-axis, I'm up here. If I cross the y-axis, I'm on that graph. That's symmetric to the origin. Those are odd functions. Odd origin, odd origin. All right. Also, even functions, algebraically, we can tell them because function f is even if and only if when the point xy on the graph of f, then the point negative xy is also on the graph of f, which means f of negative x is equal to f of x. So what we can do there is we can look at points, and as long as I have a negative x and a positive x, I have the same y value, excuse me, then it's an even function. Algebraically, I could plug in negative x, and as long as I get the same y value or the same answer as the original, then I also know it's even. A function f is odd if and only if when the point xy is on the graph of f, then the point negative x negative y is also on the graph of f. So f of negative x is equal to negative f of x. So if I plug in the opposite sign of the x, I should get the opposite sign of the y that went with the original x. And so what that means algebraically is if I plug in negative x, I'm going to get the same exact terms, but all of the signs will change. And we'll look at that in just a minute. Okay, so let's look at example 1 here. It says, determine whether each graph is even, odd, or neither. Well, look at graph A. So when I'm looking at this, I'm going to pick this point here. It's kind of got that look. So I've got something in that second quadrant, which means I should have the point that goes with it in the fourth quadrant. So I'm going to reflect across the x and then across the y. So that point works. Now I'm going to check another point because, I mean, sometimes 1 or 2 points might. So check a few more. So let's see. Let's do this one. If I go across the x-axis, it doesn't move. And when I go across the y-axis, reflect across it, there we are. Okay, I could even pick one more. So how about this point here? If I go across the x-axis, I'm up here, and then across the y-axis, there I am. I'm on the graph. So this one is odd. Okay, B. When I look at B, looks like the y-axis is splitting this graph in half, and it's a mirror image on both sides. Notice these points are equal distance or reflections. These are reflections, so this is even. Symmetric to the y-axis. Now on C, well, it doesn't look even to me because if I try the y-axis, this does not cut my graph in half, so it is not even. So maybe it's odd. Let me check. If I take this point right here and I go across the x and the y, it does match up. Let's try another one though, because remember I said sometimes we get lucky. So what if I try this top point here? So it's a little above the 3, so if I go across the x-axis, and then I go across the y-axis, there's no graph there. So it is not odd. We said it's not even, so this one is neither. All right. And then example 2 is to state if the following functions are even or odd. So this is where we're going to check them algebraically. Both of them told us that if we plugged in the opposite sign of the x, something should happen. So to find algebraically, we're going to plug in negative x for x, and we're going to simplify. Well, my original function is 4x to the 6th, and so I'm going to build that skeleton. I'm going to plug this negative x in for all of my x's, and then I'm going to simplify. Remember, PEMDAS says exponents first. So I have 4 times negative x raised to the 6th. Anytime a negative number is raised to an even exponent, it's going to be positive. Negative number raised to an odd exponent stays negative. So this is negative, 6 is even, so negative raised to an even exponent, so it's become a positive x to the 6th, which gives me 4x to the 6th. Now, I compare that back. Is that the same as the original? Yes. So therefore, this function is even. All right, let's do the same thing for B. So for B, we're going to plug in negative x. So negative 8x cubed. I'm going to plug that negative x in for the x. So I get negative 8 times negative x raised to the 3rd. Well, negative raised to 3 is odd, so negative raised to an odd exponent stays negative, so I get negative x cubed times negative 8x gives me 8x cubed. So now I'm going to compare this back to the original. Is it the same? No. So therefore it is not even. This is a negative 8, this is a positive 8. Did all signs change? So is this a negative of the original function? So did all signs change? Well, I only have one term, and here it's negative and here it's positive. So yes, all the signs changed, so therefore this is odd. Now if I'd had 3 terms, I would have to check all their signs. This was only one term. All right, let's try C. So now we're going to plug in still negative x. So 5x to the 4th. Plug negative x in there. Remember, exponents first. So you got 5 negative x raised to the 4th. 4 is even. So negative raised to an even exponent stays positive or becomes positive. And so then 5 times x to the 4th is 5x to the 4th. When I compare this to the original, it is exactly the same. So therefore, it is even. All right, let's look at example 3. It says, show algebraically to determine if f of x equals x squared plus x minus 12 is even, odd, or neither. So we're doing the same thing. It just gave us a longer polynomial. So it's x squared plus x minus 12. Plug negative x in for x, all of them, and then simplify. Negative x raised to the second, a negative raised to an even exponent becomes positive. Here we have plus a negative, which is minus, and then bring down your minus 12. I can't do anything else there, so now compare it back to the original. Is it exactly the same? No, that sign's different, so it's not even. Did all signs change? No, only that sign changed. So it's not odd, so this would be neither. In order for it to be even, it would have to have a plus and a minus. In order for it to be odd, let me write this here. So to be odd, we would have had to have a negative x squared minus x plus 12. Notice all three signs are different than what's in the original. That would be odd. All right, let's look at example 4. Show algebraically that g of x equals x to the 5th minus 4x cubed is an odd function. All right, so we're going to go plug in negative x for x. All right, so then we have a negative x raised to an odd exponent, which is going to stay negative. So minus 4 times negative x raised to an odd exponent is going to stay negative. Got to go do our multiplication right there. So I have negative x to the 5th plus 4x cubed, because a negative times a negative is positive. When I compare this back to the original, it just said show it's an odd function, so we just got to make sure it's odd. So remember, odd, all signs change. So did the first term sign change? Yes. Did the second term sign change? Yes. So therefore, we know that this was odd. Example 5 says show algebraically that h of x equals 2x to the 4th minus 6x squared is an even function. So h of negative x. All right, let's go plug in negative x for our x's. All right, simplify. Remember, exponents first. So I'm going to bring down my 2 times. Negative x to the 4th. Negative raised to an even exponent is positive. Bring down your minus 6 times. Negative x squared. Negative raised to an even exponent is positive. Multiply. 2 times x to the 4th is 2x to the 4th. Negative 6 times x squared is negative 6x squared. And then we want to know that it's an even function. So remember, even functions remain the same. So compare it to the original. Did my first term stay the same? Yes. Did the second term sign stay the same? Yes. So therefore, we just show that this was even. All right, and that's the end of 1.5b.